Hi everyone, I'm Supravat Ghoshal. In this talk, I'll be talking about approximating CSPs with outliers. This is joint work with Anand Lewis, who is at Indian Institute of Science. Now, this work primarily deals with constraint satisfaction problems. Most of us know what they are, but let me just define them to set up the convention. So, they are combinatorial optimization problems that are defined in terms of a constraint hypergraph. Here, the vertices represent variables, the edges represent constraints, and for every edge E, we have a constraint set, which is pi E, which is a subset of K cross K. This subset defines the set of labels that can be assigned to the endpoints of an edge to satisfy that edge. And as usual, the max CSP objective of an instance is to find the labeling of all the vertices that can satisfy as many edge constraints as possible. And this maximum attainable fraction of constraints, which can be satisfied simultaneously, is usually referred to as the value of the CSP and is denoted as val of psi. Now, in this work, we deal with a slight variant of max CSPs, which are called strong CSPs. So, what are strong CSPs or strong constraint satisfaction problems? Well, they are still defined in terms of a constraint hypergraph. And then we have the usual notion of an edge being satisfied by a pair of labels. But then the objective here is slightly different. The objective is to find a largest induced satisfiable subinstance. What does that mean? Formally, given a subset of the vertex set, we will say that that subset induces a satisfiable subinstance if the induced instance has value 1. That is, in other words, we'll say that that induced instance is satisfiable if there is a labeling of the vertices in the subset which satisfies every induced constraint. And in this language, formally, the objective of the strong CSP is to find a subset of largest size which induces a satisfiable subinstance and labeling that witnesses that satisfiability. Now, there are many well-known problems that naturally fit into the framework of strong CSPs. Perhaps one of the most natural instantiations of this is the odd cycle transversal problem. Here, we are given a graph, and the objective is simply to find the largest subset which induces a bipartite subgraph. Now, how is this a strong CSP? Think of the graph itself as a constraint graph, and the labels being 0 or 1, and think of every edge as a not equals constraint. Then note that for any subset of the vertices, if there's a Boolean labeling which satisfies all the induced not equals constraints, that just means that that subset induces a bipartite graph. And therefore, this allows us to reinterpret the strong CSP objective as trying to find a subset of largest size which induces a bipartite subgraph. And it's also useful to think of this as a vertex deletion variant of max cut, where in max cut, we can think of it as trying to delete edges to reach a bipartite graph. Here, we are trying to delete vertices to reach a bipartite graph. More generally, odd cycle transversal falls into the framework of a more general class of problems, which is a strong unigames problem, which is as follows. So here we are given a unigame, and we want to find a subset of largest size such that the value of the induced unigame on that subset is 1. Again, this is a problem which it describes several well-studied problems as special cases. So odd cycle transversal is directly an example of strong unigames. Balanced vertex separator can be thought of as a example of strong unigames with a global cardinality constraint, and so on. Furthermore, strong unigames itself is a natural variant of unigames. We can think of it as a vertex deletion variant of unigames, and it's also useful as a starting point for many reductions to problems which require some sort of global structure. For example, uh, the hardness reduction for of quote and reggae for vertex cover, the hardness of maximum induced bike leak by Pangla et al., the optimal inapproximability results for max CSPs of Raghavendra. All of these results use strong unigames as a starting point. Now, what we study in this work, um, in one line, we study the approximability of strong CSPs on low threshold rank graphs. So formally, let me set up the exact question that we study. So let's begin by describing what is threshold rank of a graph. So threshold rank is a very well studied parameter that's tied to the spectra of a graph. Formally, given a threshold tau, the tau threshold rank of the graph is simply the number of eigenvalues that are larger than tau in the normalized adjacency matrix of the graph. For example, if your graph is a lambda spectral expander, then its 1 minus lambda threshold rank is exactly 1 because the second largest eigenvalue of the matrix must be 1. Now, more generally, threshold rank is very nicely connected to several graph theoretic properties, and there are many fundamental results which use threshold rank in a fundamental manner. For example, there is this higher order Cheever's inequality, which uses threshold rank to give quantitative bounds on the small set expansion profile of a graph. It's also used in several spectral regularity lemmas. For example, it was used in the seminal work of Approximating, who gave sub-exponential time algorithms for unigames. It was also used in a slightly different regularity lemma in a later work of Oves, Kern, and Trevisan, among others. And with all these nice properties that are guaranteed by threshold rank, it has naturally resulted in a body of work which gives improved approximation guarantees or parallel repetition bounds as a function of the threshold rank. Of particular interest to us is this phenomena that max CSPs are easy in low threshold rank instances. This was observed in several works. For example, a quantitative statement of this phenomenon is the following: that suppose we are given a max CSP instance and the threshold rank of that instance is at most a constant. Then there exists a polynomial time algorithm which will find labeling for that instance, whose value is close to that of the optimal value of the instance, up to a small additive error depending on the choice of the threshold. Now that we know that max CSPs are easy on low threshold rank graphs, we want to understand if the same is also true for strong CSPs. For example, suppose we are given odd cycle transversal instance, which is on a graph which has low threshold rank. Then can we give better than worst case guarantees for this problem? Actually, in fact, we want to also study this under a weaker condition where we shall just require the underlying constraint graph to have induced low threshold rank. What does that mean? What we shall ask is that the full instance does not need to have low threshold rank. It just suffices if the graph induced on the optimal solution of the strong CSP instance has a low threshold rank. For example, if the optimal solution is a star, we will just ask that the graph induced on S star to have low threshold rank. Note that as such, under this condition, the full graph may have threshold rank which is linear in the number of vertices, and it's actually not too hard to come up with instances which encode hard to approximate max CSP instances. And those are instances which satisfy this induced low threshold rank property. So in this work, we actually show that strong CSPs are actually easy. Certain classes of strong CSPs are easy on low threshold rank instances. In fact, they are easy even in induced low threshold rank instances, for which we know that such instances can have hard max CSP, hard to approximate max CSP instances. Like, our main result is the following. So the following theorem says that suppose we are given a strong unigame instance which contains a 1 minus delta size subset that is satisfiable and induces a graph which has threshold rank at most log 1 over delta. Then there is an n to the 1 over delta time algorithm which will find another subset of relative size 1 minus delta raised to the 0.1, which induces a satisfiable subgraph. Now note that this result is not saying anything about providing a labeling for that subset, but that is fine because we know that satisfiable unigames is polynomial time solvable. So once we have a satisfiable subset, we can easily find a labeling which witnesses that satisfiability. Also, it's useful to compare this with known lower bounds for strong unigames in the general worst case setting. So previous works show that in a similar regime, it is unigame hard to find satisfiable subgraphs of size 1 minus square root delta log k log d, where k is the size of the label set and d is the max degree of the graph. On the other hand, this theorem is independent of the guarantees of this independent are this theorem is independent of parameters d and k. So essentially, this is saying that strong unigames is strictly easier on low threshold rank instances. In fact, even induced low threshold rank instances when d and k are large. Also, as almost immediate corollaries, we get quantitatively similar results for related problems such as odd cycle transversal and balanced vertex separator. For example, our result for odd cycle transversal is the following. Say we are given a graph which contains a 1 minus delta size subgraph that is bipartite and induces a subgraph which has threshold rank at most log 1 over delta. Then there is an n to the 1 over delta time algorithm which will find a subset of relative size at least 1 minus delta raised to the 0.1, which induces a bipartite subgraph. Again, it's useful to compare this with known lower bounds. Of previous work show that in a similar regime, it is unigames hard to find bipartite subgraphs of size 1 minus square root delta log d in the worst case setting, where d is the max degree of the graph. And again, the bound in this corollary is clearly independent of the parameter d. So this is saying that odd cycle transversal is easier, strictly easier in low threshold rank instances, especially when d is large. Now, in the rest of the talk, I will try to describe the main challenges one can face in trying to transfer techniques that work for max CSP algorithms for in the low threshold rank setting. And then I'll give a sketch of our approach and we'll briefly see how we address those challenges. Now, the first challenge is an obvious one. It's this incompatibility between a vertex deletion objective and an edge deletion objective, right? So in max CSPs, we want to kind of delete edges to reach a subgraph which is completely satisfiable. And in strong CSPs, we want to delete vertices to reach a completely satisfiable subgraph. This incompatibility obviously manifests in the techniques that are used to solve these problems. For example, previous results mostly rely on some sum of squares lifting of a standard SDP relaxation for the max CSP. And typically, these SDP relaxations only care about the number of edges that will be left unsatisfied, and they are not tailored towards trying to reduce or minimize the number of vertices which are incident on unsatisfied edges. Similarly, the main workhorse behind previous results, which is this local to global correlation property and its implications to independent rounding on conditioned SOS solutions, they are again tailored towards trying to say something about the number of edges that would be left unsatisfied after rounding of a solution. And if we try to use the same for vertex deletion problems, then they give very lossy estimates. Usually these lossy estimates end up depending on the number of degree of the maximum degree of the graph. The second challenge is again an obvious one. It's this issue that we work under this weaker assumption that the full graph does not need to have low threshold rank. We only need to have low threshold rank on the subgraph induced by an optimal solution. And therefore, any nice properties that might come out of the low threshold rank subgraph hidden inside this larger graph is not automatically inherited by the larger graph. And it's not clear how to use those properties immediately from that apply for the hidden subgraph. So these are the obvious challenges which kind of immediately tell us what to fix. And it's obvious what to fix, but how to fix them kind of requires more ideas. So as a first step in our algorithm, we ask this question that, oh, okay, we know that the full graph does not possibly may not possibly have a low threshold rank guarantee, but there is a large hidden subgraph which does. Then can we find a relatively large subgraph which has threshold rank which is not maybe the smallest possible, but still comparable to the smallest possible? So we answered this question in the affirmative. We give an algorithm which basically finds a large subset which induces a low threshold rank graph. Formally, we give an algorithm which, if it contains a 1 minus delta sized subgraph which has threshold rank at most log 1 over delta, then this algorithm will find another subset of size at least 1 minus delta raised to the 0.1, such that that subset induces a graph of threshold rank at most poly 1 over delta. There is a loss in the threshold that we can guarantee, as well as a rank associated with the threshold. But both of these are fine because they only affect the running time in polynomial factors. This theorem and the algorithm associated with it is really the main technical contribution of this work. So several things go into it. For example, we use two approximation algorithm for partial vertex cover that is used to control the degree distribution of the subgraph that we want to find. We also use a generalization of Ove's, Curran, and Teresa's work, which gave an algorithm for finding a large expander hidden inside a graph which contains a large expander. And we generalize their parts of their work to the setting of a low threshold rank, and this generalization crucially uses the higher order Cheeger inequality. Now, as the next step, okay, now that we have found a subset which is quite large and induces a low threshold rank subgraph, we focus on the instance that is induced on that subset, and then we solve a natural SOS relaxation which is tailored towards this vertex deletion objective. So what is this SOS relaxation? So For example, if we are looking at the not equals constraints, which corresponds to the odd cycle transversal problem, then the objective simply minimizes the number of edges that will be left unsatisfied under the local distribution, which is similar to what happens in max cut. But note that here the pseudo distribution is now supported over an extra label, which is star. The star label is meant to indicate the vertices that should be deleted in an integral solution. Now, using this interpretation, let's decode the remaining two constraints. The first constraint basically says that in any integral solution, at most delta fraction of the vertices should be deleted. And the next constraint simply says that in any integral solution, if one of the edges is violated, then it must be that at least one of the endpoints of that edge is deleted. Now, this is the overall relaxation. If it's a t round SOS relaxation where t is a constant, then we can solve it in n to the t time, which will be polynomial time. Finally, once we have an optimal solution to the SOS relaxation, we round off a integral solution. How do we do that? We basically use the stronger property that is guaranteed for certain predicates, which is called this conditioning reduces variance, which is strictly stronger than local to global correlation. So this property says that there exists a conditioning under which the pseudo distribution will end up having low average variance as long as it's defined on a low threshold rank instance. That just means that there is a conditioning for the distribution under which most variables will be automatically determined, almost automatically determined. And using this, we do the following use the following maximum likelihood labeling process, where we assign a label to a particular vertex depending on the masses of the local marginal. So in particular, for any vertex I, we will assign the label that has largest mass or corresponding to the marginal of label I on the condition distribution. So the overall algorithm looks like this. It's the first step is we find a large subset which has induced low threshold rank. Then after we find the subset, we solve the SOS relaxation on the induced instance. And finally, we condition the distribution appropriately and use the maximum likelihood labeling to round up a solution. And in the end, we'll delete the vertices that are labeled star. So that is our entire algorithm. I'll quickly conclude my talk by summarizing our contributions and a few open questions. So the main contribution of this work is that we show that we can get improved approximation for strong unique games on low threshold rank instances. An important component of it is this spectral partitioning algorithm, which can find a large induced threshold rank subset, a large subset which induces a low threshold rank subgraph in a graph which contains a hidden large threshold rank subgraph. And finally, the framework which works for strong unique games is actually general enough and it applies immediately to any CSP with a predicate that satisfies this conditioning reduces variance property. Now, as a last step, let me just mention some interesting, immediately relevant open questions. The first open question here is, can we get sub-exponential time algorithms for strong unique games and small set vertex expansion, which is the analog of the edge expansion problem for strong unique games? So given that we already show that strong unique games is easy on low threshold rank graphs, can use that as a stepping stone to develop sub-exponential time algorithms. The second question is that so this framework seems to work mostly for predicates which satisfy this conditioning reduces variance property. So one can ask, how can we solve strong CSPs for other predicates? And finally, Can we also give efficient algorithms for strong CSPs which work, which are which satisfy other easy to solve characterizations such as bounded tree width or minor freeness? So yeah, this is all that I had to say in this talk. I look forward to seeing you all at the conference and the poster session. Thanks for listening.